All this debugging was done in assembly language, whether it was Alpha, MIPS, PowerPC, or x86, and with minimal symbol table information, so it's not like we had Visual Studio connected. Still, it was enough information to sort out most crashes, find the code responsible, and either fix it or at least enter a bug to track it in our database. The hardest issues to sort out were the ones that took place deep inside the operating system kernel, which executes at ring 0 on the CPU. You see, the operating system uses a ring system to bifurcate code into two distinct types: kernel mode for the operating system itself, and user mode where your applications run. Kernel mode does tasks such as talking to the hardware and the devices, managing memory, scheduling threads, and all of the really core functionality that the operating system provides. Application code never runs in kernel mode, and kernel code never runs in user mode. Kernel mode is more privileged, meaning it can see the entire system memory map and what's in memory at any physical page in any instant. User mode only sees the memory map pages that the kernel wants you to see. So if you're getting the sense that the kernel is very much in control, that's an accurate picture. Even if your application needs a service provided by the kernel, it won't be allowed to just run down inside the kernel and execute it. Instead, your user thread will reach the kernel boundary and then raise an exception and wait. A kernel thread on the kernel side then looks at the specified arguments, fully validates everything, and then runs the required kernel code. When it's done, the kernel thread returns the results to the user thread and lets it continue on its merry way. There is one other substantive difference between kernel mode and user mode. When application code crashes, the application crashes. When kernel mode crashes, the system crashes. It crashes because it has to. Imagine a case where you had a really simple bug in the kernel that freed memory twice. When the kernel code detects that it's about to free already freed memory, it can detect that this is a critical failure. And when it does, it blue screens the system because the alternatives could be worse. Consider a scenario where this double freed code is allowed to continue, maybe with an error message, maybe even allowing you to save your work. The problem is that things are so corrupted at this point that saving your work could do more damage, erasing or corrupting the file beyond repair. Worse, since it's the kernel system that's experiencing the issue, application programs are not protected from one another in the same way. And the last thing you want is solitaire triggering a kernel bug that damages your Git enlistment. And that's why when an unexpected condition occurs in the kernel, the system is just halted. This is not a Windows thing by any stretch. It is true for all modern operating systems like Linux and Mac OS as well. In fact, the biggest difference is the color of the screen when the system goes down. On Windows it's blue, but on Linux it's black, and on Mac OS it's usually pink. But as on all systems, a kernel issue is a reboot at a minimum. Now that we know a bit about kernel mode versus user mode, let's talk about what specifically runs in kernel mode. And the answer is very, very little.